Hello students, welcome to Advanced Deep Learning Lab. Today we are going to see the 7th experiment, that is Generative Adversarial Network. So let us see the experiment. Now we have to use GAN model to generate either new image or video or audio. So now in this lab we are going to generate a new image. We are going to generate handwritten new images like this. Same logic you can apply to generate other files like audio file, video file. Now let me explain the GAN model. So before understanding GAN model, let us see the difference of discriminative model and generative model. So our earlier approach, discriminative model, will just do the discrimination whether the given image is cat or dog, just discrimination. But this GAN model is trying to generate a new cat from the available sample or from the random noise or new dog image or cat image. Like that, a generative model will generate a new image. See the architecture of GAN. GAN architecture contains two parts, that is generative part and discriminative part. So here G is generator model and D is the discriminator model. This generator model will take a random noise, that is Z. Based on this random noise, it generates an image, that is G of Z. That is given to discriminator. Discriminator is getting input from two different things, from generator also and from real world also. From real world data set, it takes the actual image. Now discriminator will find whether the image is real or fake. So the initial part of the program, it takes a random noise or random handwritten images. In that case, loss will be more. Then, because loss is more, we have to reduce the loss. Model will try to reduce the loss by increasing number of epoch. A new image will be generated. It will look like a real image. So the objective of generator is, it has to generate an image that discriminator should not be able to identify as fake. So it keep on process based on the loss function. Now this is the architecture model, deep learning architecture model of GAN. So the generator model is like this, left side, and discriminator is right side. Generator model you can understand, similar to the previous block diagram architecture, it takes a random value here, random noise value. Here for example it is given 100 Z, means 100, 1 to 100, any random number from normal distribution it is taking. And here it is doing deconvolution. Convolution 1, convolution 2, 3, 4. 4 convolution layers are there here. From each convolution, it is doing upscaling of the image. So from the random noise, it upscales, then upscale to convolution 3, then upscales to convolution 4. That image is given to discriminator, this side. So the discriminator will try to identify whether the image is real or fake. Discriminator is already trained with real images. So if real image comes, it takes 1. Fake image comes, it takes 0. The output will be 0. So the objective of generator is, it has to cheat the discriminator by simulating a realistic image. Whereas the objective of discriminator is finding whether the given input is real or fake. Now in our lab program, we are going to take MNIST dataset, that is handwritten numbers dataset. similar to this 1 0 1 0, like that handwritten images are there. There are two parts, discriminator part and generator part. The variables are here. X is your sample data, that is from real world data. P data of X, that is the distribution of real data, the entire data set. Whereas P of Z is generated distribution. So we have a random noises here, then Z is sample data. So this Z will be taken from generator and gives to discriminator. So discriminator will identify whether the image is real or fake. 1 means real, 0 means fake. It's not an exact binary value, so it may be 0.90 or 0.80, in the sense 80% real. Or if it comes 0.2, 20% fake. Or 20% real, remaining is fake, so near to 0. So like that, the GAN will identify the real image and fake image. Now how it identifies? Based on the loss function. So initial time, from the random noise, the generator gives an image, random image, that will not look like a handwritten image, definitely loss will be more. So that loss values are calculated using this function, min max function. So the objective of this function is, it is minimizing your generator loss and maximizing your discriminator objective, maximizing your discriminator output. The formula is expectation of X P data, that is the real world data, log D. D is a discriminator value. So discriminator should be maximized, where generator should be minimized. So after many epoch, the generator will generate an image, looks like a real image. So discriminator identifies that image as a real. So after running our program, it will look like this. So initially some random noise will give. Sample 16 images are taken. After some epoch, images are looking like this. Then number of epochs are increased. It will come like this. Then again number of epochs are increased. So finally we may get a image like this, handwritten images. It may look like a real image. So let us go to the program. Okay, to refer this program, you have a website. You can refer this website, tinyurl.com ADL GAN. So go to this website. The program is available. Now let me explain the program. This is the program. So the first cell is installing TensorFlow version 2 and some image file. Then the second cell, some other important library and TensorFlow files are installed here. Keras we are installing, PAL, Matplotlib. So these are the basic installation file. And here we are loading the MNIST dataset. So we know MNIST dataset, that is I'll type MNIST dataset here. So MNIST dataset contains handwritten images, 60,000 images. The training images are taken in our program. So this line takes the dataset, assigns to train images and labels. 0, image is 0, label will be 0. Image will be 1, the label will be 1. So like that, dataset is assigned here. And the next line, the image is reshaped to 28, 28, 1. So horizontal X side 28, vertical Y side 28, and 1, it is black and white image. RGB images will be 3. Then the next line, we are normalizing the images to the range -1 to +1. So the image size is 128. it is normalized to -1 to +1. The buffer size 60,000, that is the training images, and batch normalization will batch wise we are giving training, so batch size is 256. And the training data set is taken here. It is shuffling the images and taking. Normally we used to give 80-20 like that. So we don't take test images here, only train images shuffled and taken. Now here model is generated, next cell. There are two parts we have, generator model and discriminator model. Now we'll see the generator model. The generator model contains convolution layer. We'll see the slide once again. Here we can see this is an example figure. Same number of convolution is not required. Now see in the program. Here we have convolution layer here. It's a sequential model. 7-7-26. So initially the image is taken 7 horizontally, 7 vertically, and 256. So we input 100 random noises are taken. Batch normalization and leaky ReLU activation is given. We are doing deconvolution here. And here is the layer 1, here is the layer 2, here is the layer 3. And all the layer has batch normalization and leaky ReLU. Final output will be 28-28-1. Horizontal, vertical, 28. And it's a black and white image. The model is returning here. Now we'll see the summary of the model. So dense layer output 7-7-256. So the shape is 12,544, and we have the convolution layer 1 here, deconvolution layer 1 here, and here do second deconvolution layer, and here the third deconvolution layer. So the final image 28-28-1 with random noise is given here from the generator. So this image is given to discriminator. Discriminator has to identify whether the image is real or fake. The first image, definitely it's a fake image. Discriminator can easily identify. So let us take one sample here, sample noise. This is the random noise, 1 to 100 we are printing. And let us see the image, how it looks like. So the initial image will be like this. So the first noise image we are giving. The discriminator can easily identify this image is not a handwritten image. So by training the model, by increasing the number of epoch, finally we will get handwritten images similar to real images. Now discriminator model, similar to this architecture, layers are designed. And here the first layer, and here one more layer, convolution layer, and just we are giving flattening the output and giving to the dense layer. So the here final output is either 1 or 0. The dense layer will give final output as 1 or 0, mean real or fake. Now discriminator and generator part is defined. Here summary of discriminator model. It shows the parameter of convolution layer, and the last one, dense layer, single output is giving. So the decision, now still the model is not trained. So the initial decision will be 0 only, means it's a fake image. We have given one random noise image that is not looking like a real image. So the output will be 0. Now loss will be more. We should reduce the loss. So loss function we have checked in the PPT. The cross entropy, first real loss. So loss will be from discriminator as well as generator part. From discriminator we are getting 2 loss, and generator we are getting one loss. Because discriminator is getting real images and duplicate images. So real loss is calculated, the fake loss calculated, total loss is returned here from discriminator. And generator is giving a single loss function. Based on the both loss function value, we'll train the model, we'll reduce the loss. And we have used ADAM optimization for generator part and discriminator part. So based on the gradient value and learning rate, we'll reduce the loss. Now there is one checkpoint here. This cell will create a checkpoint between every epoch, just to save the output, how it look like. So later, I have already executed the program. This checkpoint figures are available in the folder. So after running this, you can see the images in between different epochs, how the image was looking. Now here, number of epochs are 50. Initial noise is 100. Seed value. These are the seed value. Now we will train the model. So here we are training the model. So this function takes the input. Here loss is calculated. So based on the gradient, it is reducing the loss. Now this function should be called inside this train function. That is train step. So a separate function is defined, train step. The train step is called inside this function, train. 50 epoch, for 50 epoch, this loop is running and calling the above function. So it keep on reducing the loss. So after reducing the loss, we'll generate the image and save. So the final image, handwritten images generated by GAN will be saved using this code. Now this is the final image. Once you run this code, it takes some time, 3-4 minutes it takes. This is the finally generated sample images. Sample 16 images we have taken, and almost it looks like 6, look like 1, but these images are not good. And here these images are not good. Here somewhat looking like 3, 6. So it means number of epoch should be increased. So you can increase the number of epoch and check the output. So we are saving this checkpoint, the last one. So the same checkpoint value, we can continue our execution. Now randomly we'll take one sample from in between. When 50 epoch was running, how the image was here. So the random noise was given. From that, the model has generated numbers like this. From here, after 15th epoch, we have got these images. So to get more clear image, we should increase the number of epoch. The entire operation is saved as a GIF file. Once GIF file is saved, this animation file you can open and you can see how the image was displayed in every epoch. That will be shown in this GIF file. It will be saved in your root folder. Or if you are running in your laptop, in your root folder, you can download that file. So one sample image is taken and displayed here. This is almost looking like 0. So to increase the accuracy, we should increase the number of epoch. Okay, that's all in this program. So this GAN program trying to generate a handwritten images of numbers from 0 to 9. And the real images are available from a dataset called MList. And the output you have checked. So do practice this program and upload your output. That's all in this lab. Thank you, students.